if you make, just a simple assumption that you accelerate, you have as much energy in relativistic protons as you have in relativistic electrons that produce the photons. Now, the question is now, do we have enough sources within the GZK radius? Okay, so we have enough sources within the universe, but within the GZK radius, because they don't propagate from much beyond that at the high energies. And so you can estimate that in order to explain the observed events, you require at least 10 to the 4 sources, all sky within the GZK radius, in order to have a non-repeating type of event. So far, we don't seem to have any repeaters. So you need about 10 to the 4 sources within the GZK radius, so source density of 3 times 10 to the 4 per megaparsec cubed, and all that within a GZK radius. That, at first sight, seems to be a problem, because the number of normal galaxies, the density of normal galaxies is plenty. There are plenty of them. The density of active AGNs is adequate, but the density of GRBs within, is much less. So you have fewer within the GZK radius per unit time. So in other words, within 100 megaparsecs, you consider how many GRBs have occurred within the GZK radius in the past 20 years, and maybe none have occurred. But the point is that the cosmic rays, being charged particles, will diffuse. And so there is a diffusion time, and the diffusion time is of the order of 10 to the 5 years. And so you have to count how many GRBs can have occurred within 100 megaparsecs, not in the last 20 years, but in the last 10 to the 5 years. And in the last 10 to the 5 years, there are enough GRBs that have occurred. So you do the correction, you take the original number, you multiply it by this delta t, and then you get the right density estimated. And flaring AGNs could have done the same thing. So really, all you're saying is that either AGNs or GRB satisfy the density of sources within the GZK radius. It doesn't tell you which of them it is. But if you have a source that makes a slope -2 type of spectrum, you could explain these, the ankle portion of the spectrum. So these are the examples for the GRB contribution. You could explain why you make a transition from the previous, let's say, low energy spectrum to something which causes the need. There are other explanations, like Berezinski's so-called explanation with Bethe-Heitler interactions. So again, it's 2 types of interpretations, not very easy to sort of distinguish between them, at least with cosmic rays. But here is the cosmic ray spectrum. In a GRB scenario, here is the contribution to the cosmic rays of GRBs, and this is the observed Fourier spectrum. And this is the contribution of AGNs. So these GRBs with a spectrum of -2, and these AGNs with a spectrum of -2.7. These with an evolution, a cosmological evolution, 1 plus z to the 3.4, and these no cosmological evolution. So you can fit the cosmic ray spectrum with both an AGN scenario and the GRB scenario. You couldn't tell the difference. But if you look at the diffuse neutrino flux predictions of the 2 cases, they're different. So you get from the AGNs a larger neutrino flux. So that's why it's important to do, to see if one can combine the GZK neutrino observations with GZK cosmic ray observations. And so predictions have been made. So these are prediction by Berezinski's group. The red is his AGN model, and the blue is the GRB model. And these are the gamma ray predictions compared to Fermi-Lat, so they don't, they're not constrained by Fermi-Lat. These are the cosmic ray predictions. They both contribute here, although the AGN model is able to better predict the lower energy cosmic rays. The GRBs can only contribute the highest portion of the cosmic ray spectrum. And there are the two neutrino predictions, which so far IceCube doesn't constrain, but it's approaching. Okay? Different calculation of the same type of thing, but here done also for not only protons, but also for hydrogen and helium and iron. And so evidently for different compositions, you get different neutrino spectra. So since the total energy of the cosmic ray is the same, when you have a composite nucleus, your energy per nucleon is smaller, and so the neutrino energy gets smaller and smaller. So you get less and less constraints, neutrino constraints, from heavier composition. All right, so going back to GRBs, if we were to detect neutrinos from GRBs, that would be a smoking gun of protons. And we might detect it either through the neutrinos, but they would also contribute to the gamma ray, because you will also have pi-naught branching ratio. Now, at the simplest level, you can consider that you have an acceleration region, which is the dissipation region, either a shock radius or a photospheric radius, and maybe a Fermi acceleration and magnetic reconnection. You inject a power law spectrum. Index is probably around -2. And then, of course, the accelerated leptons will produce photons, and then the protons will interact with those photons through the delta resonance mainly, although it's not only at the delta resonance, but above that too. And then you will get a power law of neutrino spectrum, which depends on the GRB parameters. How much energy you put into protons, how much energy you put into electrons, how much energy you put into the magnetic fields. These quantities have been estimated and have been fitted already previously over the past 15, 20 years, just from the gamma ray side. So these numbers, you don't have to cook them up now. They all exist. They've been calculated before. You just have to use the numbers you deduce from the gamma ray observations and apply these to these cosmic ray acceleration mechanism. The other two parameters are the total burst energy and the Boltzmann factor. And so if you have a proton power law and you have a broken photon power law, then these protons interact with those photons. So at the delta resonance, right, you sort of have to, the energy in the center of mass has to exceed the delta resonance energy. So these protons interact with those photons, these protons interact with those photons, and your neutrino spectrum looks like that. It's a broken power law that reflects the broken photon power law. There is a second break where the pions and the muons cool due to synchrotron or inverse quantum radiation, so that you get the second break here in the well, these occurs at 10 to the 17 or 17.5 eV. These occurs at around 10 to the 15 eV, so PeV energies. And so the original calculations, as Waxman and Bacall did, 97 and 99, predicted a diffuse, so from many GRBs, let's say, you get a diffuse neutrino flux that looks like that. That was the Waxman-Bacall bound deduced from cosmic ray observations. And these was what the internal shock would have predicted. So Waxman and Bacall used an internal shock, a traditional internal shock, a simplified internal shock model, and that's a simplified neutrino internal shock model. The external shock, the reverse shock, produces a high energy component because the photons are the optical photons of the reverse shock, and therefore you need higher energy protons to interact with them. They make higher energy neutrinos. So these are PeV neutrinos, and these are ZeV neutrinos. All right, so IceCube, of course, is in the business of looking at these. IceCube is in the South Pole, and so it's a nice place. There's deep ice, there's very good infrastructure. Why go to the South Pole? You could say that it's because, all you can do is you can work, there's nothing else to do. And so it's, it's a bunch of strings, 86 strings with phototubes, which start at a depth here of 2 kilometers and they go down another 1.6 kilometers. So there is the instrumented volume. And there is a subarray called a deep core array where the strings are much more closely spaced. The threshold for the main array is it's around 100 GeV. Well, more like a few hundred GeV, but the deep core array gets down to about 30 GeV. And now there is an even deeper subarray called Pingu, where they're trying to get down to about 1 GeV. So construction was finished in 2011 or so. And so essentially it's a neutrino telescope. What it measures is, so if you have a muon neutrino, you have an interaction of the muon neutrino with ice, you produce a muon. The muon is moving relativistically, and the ice has a refractive index, so the phase velocity of the light is lower than the velocity of the particle. You get Cherenkov radiation, and so you measure with the phototubes these Cherenkov radiation. And so the problem is that there is a lot of noise. So you have atmospheric, so you have a signal, an astrophysical neutrino coming in, interacting with the array, and you prefer to get neutrinos that are coming through the Earth, because from above you have a lot of cosmic ray atmospheric muons that are noise. So looking at it from the other side, you get your atmospheric neutrinos are coming in from above, but it's the signal neutrinos that you look at from below. And so that reduces the noise significantly. So the downgoing neutrinos, you get a much stronger signal. Now, there are other neutrino telescopes that are in preparation. Antares is in the Mediterranean, in the south of France. It's a smaller array, so it's a prototype, which the IceCube people like to say that they have a better life, but you cannot trust their results, quoting some character from Hollywood films that some of you may have heard about. But the Antares array is actually just a prototype for a full kilometer cube array, KM3net, which is being built. And so it's a much larger array, comparable in size or even somewhat larger than IceCube, and it's in the northern hemisphere. So it's ideally located for looking at neutrinos from, let's say, the galactic center. And it's complementary also in the sense that the scattering length and the absorption length is different. So in the water you have an absorption length, a scattering length, which is longer than in ice, but you have an absorption length which is shorter than in ice. So in ice you have, it's clearer. In water there are contaminants, there is potassium-40 radioactive decay, so you get somewhat more noise. But you get a better angular resolution because the scattering length is better. So these an artist's conception of how these would look like. The domes, the digital optical modules are also much more sophisticated than IceCubes. Each dome of IceCube has only one PMT. The domes of KM3net are designed to have multiple domes, so they'll have a very good angular resolution. Now, realistically, what kind of neutrinos you expect? Well, I told you that it's these combination here, and if you just look at what happens, ions produced through the delta resonance, then D is the resonance condition. So the break energy of the neutrino spectrum corresponds to the proton energy break. And so I mentioned that D is the shape of the spectrum that you expect. And it's not the only type of neutrinos you expect. It turns out that if you have a core collapse GRB, you will also have so-called thermal neutrinos. So the previous ones, these are TV neutrinos, that's here an energy that is going up from TV to PV, and that's where your ice cube is the most sensitive. Well, actually, you expect also 10 to 30 MeV thermal neutrinos just in any core collapse supernova. Right? You also get neutrinos here, even though the central object is a black hole, but you get the neutrinos there, etc. And these neutrinos, you know, they can be detected. Super K has detected neutrinos from supernova 1997A. Actually, IceCube can detect such supernova thermal neutrinos too, but it only gets the timing, it doesn't get the directionality. You just see all the noise level in all the phototubes to go up and go down. And so it's actually, it gets very good timing because it has, you know, it's a very large area. But it can only get such a signal from about 50 kiloparsecs. So the Large Magellanic Cloud is the maximum distance to which you could detect a supernova, a normal supernova with IceCube. Or a GRB, the thermal neutrinos from a GRB, if it were within 50 kiloparsecs. And it's a very unlikely event. Now, the proton-neutron decoupling also, as I mentioned, leads to inelastic collisions. That will also lead to neutrinos. In fact, those are neutrinos of 30-40 GeV. And in fact, these decoupling neutrinos were much of the motivation for building the deep core array in IceCube. So when the proposal was being submitted to NSF, the science justification included as one of the leading items these you know, signal that you could expect. In fact, you expect that as the jet is propagating through the star, the neutron-proton decoupling occurs while the jet is still inside the star, and so these neutrinos, they could be, these 30-40 GeV neutrinos could be a precursor, a neutrino precursor of the gamma ray burst. So the gamma rays occur after the jet has emerged from the star, so somewhere here, but the 30-40 GeV neutrinos occur down here, so they travel essentially at the speed of light, so they would arrive before the gamma rays. So these precursor neutrinos were, you know, the thing that was one motivation for deep core. You could have jets that never make it out, that never emerge from the star, and these would be choke jets. Then they only would have these neutrino signal, no gamma ray signal. Of the successful jets, they would have a precursor neutrino signal and then the gamma rays. All right, so then the bulk of the gamma rays, those TV neutrinos that the Waxman-Bacall model computes, are from the successful jets that make it out outside of the star. Optical medium, let's say internal shocks, and you get your neutrinos from this region. Now, IceCube has been looking for these signals. In fact, they've been using essentially the Waxman-Bacall model, and or a version of the work done by Daphne Guetta, and they came out with results. And the results was that with the preliminary array, the IceCube 40 and the 59, so 40 string and 59 strings combined, a surge from 190 GRBs, the simple Waxman-Bacall Guetta model predicts a diffuse flux of that much, and that was the signal that the upper limit of the signal. So they didn't get any neutrinos, and this was the upper limit that they obtained. So down by a factor of essentially a fourth below the model. So something that looks like a significant constraint on the simple model. You can also do a model independent constraint. You can say that let's argue that these GRBs, okay, these 190 GRBs contribute to the GZK cosmic rays. What would be the neutrino flux they would be producing? It would be something like that if they have some shock radius. Instead, all that is allowed is these regions here. So these also rules them out in a more model independent way. But it's really all based on an internal shock structure. You assume that there is a shock which accelerates, the same shock accelerates the protons that is producing the neutrinos and the cosmic rays. So the conclusion was that they called it the Fireball model, but more accurately they should have called it the standard internal shock model, over-predicts by a factor of 4 the neutrino flux. And the model independent fit also over-predicts it by 2,3 sigma. So if the GRBs contribute most of the GZKs, then they would have over-predicted the neutrinos. Now, you get this kind of limit if you assume a certain ratio of L proton to L electron energy, and they assume the value of 10, okay, which is 10 larger than the original Waxman-McCall number that they used. And so this was a somewhat arbitrary assumption. If you reduce it by a factor of 4, then of course you don't get the problem. So you can argue that the proton load is less, or the efficiency of neutrino production is less. But it's a very significant first achievement by IceCube. It's the first time that you have conservatively stated that you have a simple astrophysical model, you can constrain it with IceCube, and you can get interesting constraints. So it's doing astrophysics with neutrinos. Now, there are things to note. First is that the internal shock model is expedient, it's easy to calculate. That's the main reason why all the observers use it. But, as I mentioned, for the past 10, 15 years, in fact, it's been known, just from the gamma ray aspect, that there are problems with the internal shock model. So really, one is using a model which has its difficulties, and therefore, maybe it's not surprising that it also has difficulties with neutrinos. Then also, we don't know what's the acceleration rate of protons versus electrons. They used a factor of 10, but it could be less than 10. 10 is a maximum limit that you can get because the GRB then wouldn't be able to provide more energy. That would exhaust the whole energy budget of the GRB, but you could reduce it and still get something, which produces neutrinos, but maybe not what they tested so far. And then there are the alternatives to the internal shock model, which are, I mentioned, photospheric models or improved hadronic models, etc. So neutrinos may still be observable from GRB, but not obviously at the level that is currently tested by IceCube. Other models actually predict lower neutrino fluxes. Even if you consider the internal shock model, it turns out that it was a simplified version of the Waxman-McCall model, which itself was simple. So these were a simple model, and the IceCube people took an even simpler version of it. So they assumed that the ratio that all the neutrinos came from the break energy point in the spectrum instead of integrating over the low energy branch and the high energy branch. So that right there gave them a factor of 8 larger. So if you correct for that, then your flux that you expect is 1/8 lower. And then they also neglected the business of, so that was an overestimate of the flux just from having considered the simplified spectrum formation and all of it caused by the delta resonance at the spectral break energy. In addition, they ignored multi-pion production above the delta resonance, kaon decay, etc. Various calculations were made, and in particular these, Humer et al., they showed that this is the simple calculation, the simple initial calculation of IceCube people. Now, if you include things like the good spectral effect, the shape revision of the spectrum is that, then you have to correct for the fact that FC that they approximated the photon energy by the break energy. Then there was a rounding error in one equation. Then 2/3 because they neglected the width of the delta resonance. And then another correction because the energy losses of the secondaries, etc. So finally, the internal shock model predicts these much, which is down by a factor of 30 below the original model estimate of ice cube. If you do a numerical calculation instead of just analytic, if you do a numerical calculation, then it's somewhat above the analytical one, but still way below. And so this was pointed out also by other people, Lee, Chou-Li, and Haning He, and by Humer et al. So the ice cube 40 limit and the ice cube 49 limit was that. The more realistic limit is something like these and these, the 1 sigma error bar and the 2 sigma error bars. So really, if you want to test these particular standard internal shock model, you would have to observe for at least 5 years, maybe 10 years before you constrain it. And that is using the internal shock model, which, as I mentioned, is problematic. Probably we need to use a different model. So, as I was saying, internal shocks have difficulties. We don't know what's the relative acceleration rate, and so we should look at the alternatives. One other thing is that all these calculations, Waxman, Bacall, Gitta et al., Humer et al., Lee and He et al., they all are steady-state time-independent calculations. Of course, GRVs are time variables. If you get a shock, the shock is moving, it expands, the density decreases, so the mean free path gets longer and longer. So in a time-dependent calculation, you should get a different result. And so a time-dependent calculation is one that we did with Katsuoki Asano. Again, we just took the standard internal shock model just to see what happens. And we took the distribution, so the internal shock's radius is given by the variability time scale multiplied by the Bulk-Lorentz factor squared. We know that there is a distribution of variability time scales observed, so these are the observed distribution of variability time scales. So we considered bursts which have all these distributions, and then we consider a distribution of the luminosity, so this is the Vanderman and Piran luminosity function of bursts. And to simplify things, we assume just a single Bulk-Lorentz factor, and again a proton load of factor 10, since that's the same that I can use. And then we perform these Monte Carlo cascade calculations, Katsuoki's code, assuming that at the shocks you accelerate cosmic rays. And so you accelerate protons, but you know that the protons, as they get accelerated, they're still trapped in the magnetic field. So typically one can consider, what happens, is there adiabatic cooling of the protons as they escape or not? So we use two approximations. One of them is that there is a sudden release of the charged protons, cosmic rays. The other is that in the interaction, the p-gamma interaction, they become neutrons, and that they can escape. And after they escape, so they're not subject to the magnetic field, they escape, then they decay back into protons and they become the cosmic rays. So there are these two cases, the neutron conversion and the sudden release approximation. And so the spectra that we get for different luminosities of the burst, these are the photon spectra, okay? And these are the neutrino spectra for the different luminosity GRVs for one given variability time scale that we calculated for all the variability time scales. And then there is the neutron spectra are the black things here. So here's the escaping neutrons. And so in the neutron conversion model, then the diffuse flux of the diffuse cosmic ray flux is this gray shaded zone, 1 sigma error bars, compared to the observations. So it's within, it could contribute 20–30% of the highest energy bin. 10 to the 19.5 to 10 to the 21 on the side.